We will now start a series of lectures on computer organization. The first lecture in this series will be on the bus structure. A digital computer consists of a large number of hardware components. For proper functioning of a digital computer, all these hardware components have to be interconnected properly. In the process of interconnection, the outputs of some of these devices are connected to the inputs of other devices. When we connect the output of some of the devices to the inputs of other devices, it is possible in that process that the output of one device may be connected to the output of another device. As per the logical reasoning of the electronic circuitry, the output of any logic circuit should not be connected to the output of any other logic circuit. In case it is connected, the actual logical output is the logical ending of the two outputs of these devices, which will not perform the proper logic. To ensure that no output of one logic device is connected to the output of another logic device, although each one of them are connected to the inputs of other devices, and in the process they get connected together, we have to adopt a new technique. This new technique is what we call as a bus structure. Before we go into the details of the bus structure, we will first explain briefly about the various components that are present in the digital computer. Before we go into the details of the bus structure, let us briefly understand the function of each of the registers that are present. The input register, this is used to input data from peripheral input devices into the computer. It is basically a shift register of appropriate word length, generally 8 or 16 bits, which has a facility of parallel loading and serial shift. The second register is output register. The output register is also a shift register like the input register of appropriate word length with facility of parallel loading and serial shift. This output register is used to transfer the data from the computer to some specified peripheral device. The next register is the program counter. Program counter is a shift register used to store the address of the next instruction to be fetched and of course executed later. It will have the facilities to clear the register to 0, to increment the register contents and to load the register from some other source. The next register is the address register. Address register or memory address register is used to store the address of the memory whose contents have to be read or written under the instructions of read or write signals. The memory address register will also have the same facilities as the program counter. The next register is the data register. Data register stores the data for many applications. The data to be entered into memory or the data that is read from memory are the data items usually stored in this register. The contents of the data register may be transferred to any other register under program control with the help of the bus structure. The data register will also have the facilities of clearing it to 0, incrementing the register contents and loading into the register from the system bus. Accumulator, this is a very important register. Accumulator is another register associated with arithmetic and logic unit. Accumulator is used to store the results of arithmetic and or logic operations performed by the computer under program control. It is possible to transfer the contents of accumulator to any other register through the system bus. Accumulator will also have the facilities available for any shift register. Next is the memory unit. The memory unit, which is an essential part of any computer system, will have read and write controls, a memory address register and a memory data register. Whenever it is required to read the contents of memory, the memory read signal is enabled, the address of the contents are transferred to memory address register and the data that is read is transferred into the memory system bus. It is also possible that the data was read out may also be transferred to one of the registers through the system bus under the control of the program. The memory write operation is the inverse of the read operation, that is, data is written into the memory at the address specified by the address register by means of the write signal. We will now briefly talk about a simple tri-state logic device. To avoid interaction between the outputs of the various devices connected, the output devices have to be of the tri-state logic type. A typical tri-state AND device along with its logic is shown in the slide. A and B are the inputs of a simple AND gate. The control is another input. As per the table, a tri-state logic device has two output logic states, 0 and 1, and also a third high impedance state. The high impedance state at the output will ensure that the output of the logic gate has no effect on the input of the device to which it is connected. Such tri-state logic devices will exhibit high impedance when the control input is 0 and operate as normal logic gates when the control input is 1. Tri-state logic devices are available for all the types of logic devices that are generally available. So, you can either use a normal logic device or a tri-state logic device at the appropriate point depending on the requirement. A typical interconnection of the 4-line bus is shown in the diagram. We will now show a typical bus structure of interconnection for a 4-line bus. The same diagram can be expanded for any number of lines, whether it is a 8-line bus or a 16-line bus or a 32-line bus. For simplicity, we have shown a 4-line bus here. This structure, as seen, consists of 8 registers named A, B, C, D, E, F, G and H, each one of them of 4-bit wide. Depending on the control signal S0, S1 and S2, one of the 8 registers is selected and put on the bus. As shown in the diagram, there are 4 multiplexers named MUX0, MUX1, MUX2 and MUX3. The 4 outputs of each of the registers A, B up to H are connected to one out of the 8 inputs of these multiplexers as shown in the diagram. The diagram shows the interconnection of only one multiplexer, that is multiplexer 3. As seen there, the multiplexer 3 has 8 inputs and it receives one input from each one of the registers A to H. The other connections that are not shown are multiplexer 2 will also receive 8 inputs from each one of the 8 registers. Multiplexer 1 will also receive 8 inputs from each of the shift registers and so on. By suitably selecting the common control signals of the multiplexer S0, S1 and S2, it is possible to select one out of the 8 registers onto the common bus of 4 lines. In general, a bus structure will multiplex n registers each with m bits output to produce a m line common bus. The number of multiplexer needed to construct the bus structure is m, that is the number of bits in each register. The size of each multiplexer is n by 1 with p control signals for each multiplexer such that n is equal to 2 raised to the power of p. If the data in register A is to be transferred to the register B, the register transfer statement A to bus and bus to A are used, or sometimes it is combined and written as A to B, implying the presence of a bus structure. A bus structure constructed with multiplexers require number of multiplexers and hence is felt as inconvenient in some applications. An alternative approach is to use special type of logic devices called tri-state buffers at the output of each signal, which have 3 stable states. Many standard logic functions are also available as tri-state logic devices.